I am Olumide. Some people like to call me Dr. O. I don't like it. I like Olumide. I like Olumide. I've been teaching for so I've been teaching for a while. Currently I still hold a teaching gig at a university in Paris called ESIEE, where I am an adjunct professor, a part-time adjunct professor there. I teach data science. I also teach machine learning. So yeah, and I've also had foray with AI Saturdays. I was here last year. So, like I said, this is a class, but we're here to gist. So don't hesitate to stop me. I've taught machine learning for a while and I know how difficult it is. And I know, I remember my glasses. Sorry, I don't look like a nerd. I can't see. So I know how difficult it can be, and I know how sometimes the concepts are just so weird that, you just ask yourself, what is all this? I have a beef with mathematics and the way machine learning is explained nowadays because we tend to focus on the maths and we forget about the intuition. But the thing was, the intuition, the intuition is what the maths is trying to summarize. And now the maths has become a hindrance rather than a help. So for people who are familiar with mathematics tools, yeah, it's easy because I can look at a formula and I can say, yes, I understand what's going on. So you can look at the maths and then you can say, yeah, I know what is I know what is going on if you know how to interpret mathematical formulas. But if you don't, then you just say, what is this? What is all this? And then it chases you away. So I would focus on the intuition, and I would say sorry to people who are mathematical geniuses here who expect something more complex. But I want us to drill down into understanding why we're doing what we're doing. And you can always go back to read the maths, or you can always send the paper to me and I'll try to summarize. Or you can always say you want to have a 10-minute discussion of the mathematics with me and I'll try to make that time available. But the thing about it is the intuition is something you won't forget. And I try to do that with stories. So this is what I'm going to do a lot in this class, where I'm going to try to tell a story around a concept and try to make sure that we get the story, we can forget the maths and get it and come back and remember. But the intuition is what stays with us. And especially when I started teaching abroad, where when I'm giving my students an exam, I give them the formulas on a different sheet of paper, and then I give them the questions. You start to understand that no one cares to remember formulas or stuff because you can always go back to a textbook and find the formula. It's the intuition that keeps us going. Also, something you should remember about linear classification and about, I would say, machine learning in general, is that it is the science of drawing lines. If there's anything you remember, or if you want to go and you have an interview and then somebody says you should explain machine learning, you can just say, oh, it's the science of drawing lines. I remember an interview I had where somebody asked me to explain gradient descent to my grandmother. At that point, it was the intuition about it. But in a sense, if there's anything you remember about machine learning linear classification, just think about the science of drawing lines. And this is, think about this as an art class where we try to teach people how to draw lines and lines of separation. Are we good? I hope I haven't lost anybody yet. Okay, right. So when I started my AI school, it was very interesting. First day, I was the only Black person. This is 2013 in the UK. They had picked 16 people all around the world, and they were in this class. Everybody was a nerd. And the teacher walks into the class and says, oh, I want to teach you machine learning. I give you an example of linear classification. Imagine a Nigerian prince sends you a message. No, and everybody in the class just turned and looked at me. And in a way, that was really an interesting way to start a class, because First of all, I was not just the only African. I was not just the only Nigerian. I was the only African in the class. And here we're talking about spam messages with reference to Nigerian princes. So let's do an introduction here around, what are we doing when we think about linear classification? What are we trying to do? So you have thousands of credit card applications. Fintech is very big in Nigeria these days. And you really want to assess, who will default and who will not default. We don't do a lot of credit card. I think we're getting there now. For instance, on Kuda Bank, Kuda Bank has to decide who gets overdraft and who doesn't get overdraft. A couple of my friends last week realized how much of overdrafts they give me, and they were like, "Oh my God, how would they give you this kind of overdraft?" But for them to give a person overdraft, they have to ask themselves, is this person going to default? Or is this person not going to default? Is this person, going to run away with our money? Or is this person going to stay? I don't know if people remember the Pampe jokes and the Pampe era, if Pampe wants to say, okay, fine, we want to know who is going to return money before we give them. You have to be able to separate between the safe clients and the potentially risky applications, potentially risky applicants, right? So you want a linear line. You want to say, okay, there's a line. Okay, so let's put everybody somewhere, right? And then you draw a line. People on the left, risky. People on the right, potentially not risky. And these are the kinds of lines we have to draw every day in our lives. Think about every time in your life you need to make a decision. Now, every day we make decisions, and we need to make these clear-cut left and right decisions, right? Every day we are doing a linear classification. Every day, right? Even when we're driving, you say, okay, fine, I need to turn left. Should I turn left or should I turn right? Should I go or should I stay? At this point, you are faced with a lot of binary decisions in life, and then you have to make a decision. And if you want to translate that into creating machines or creating models that can mimic humans, one of the most fundamental things that you have to be able to give them is they're able to make binary decisions, efficient binary decisions. And I know you're going to do non-linear, right? And maybe in the coming week or in the coming couple of weeks. But one of the things I like about linear classification or thinking about things in the linear sense of it is this. I think I made a LinkedIn post about this some weeks ago, where I talked about non-linear being solvable using what in mathematics we call piecewise linear. So in a way, if you have a non-linear problem, you can break it down to very small chunks. And within those small chunks, you're going to have linear decisions to make. And then you can aggregate those linear decisions back together and essentially solve a non-linear problem. And I know that might be a bit difficult to grasp now because maybe you haven't seen the mathematical concept of piecewise linear, all of that. But yeah, essentially what neural networks does. So that is what it does in a sense. So now neural networks or deep neural networks is all of them is just aggregating linear solutions and making them solve nonlinear problems. So in a sense, this is also what humans do. I mean, that's maybe an oversimplification because I've really met some complex people in this life. But in a way, our life is all about, making, simple classification, simple linear problem separation, simple linear decisions at any given time, right? Even probably, I checked it. Teju is going to be doing probability. I think she's going to do something about probability. Even on some level, I've had to have these talks. I have a lot of friends who are nerds, so we do some of these discussions. And one of the discussions one time was someone was essentially trying to say that probability is not, there's a non-linear element. And I say, yes, there might be. And so there's something we'll see with logistic regression when we get to it. There's a non-linear element to it, but it essentially translates into a linear decision, right? So in a sense, when you have a probability of 0.5 or greater, you say, hey, okay, this looks good. I might do it. Or if you have 0.4 or lower, you'd be like, no, I'm not going to do it, right? I'll tell this one story before I go forward. I was at a conference and someone asked me a question. It's like, was there an interview? I can't remember. It was like, can you explain, can you explain Bayes' theorem without the mathematics? And I said, so imagine you met somebody and you're like, oh, I could marry this person, right? And all you had at that time was what we call prior probability, because all you had was prior information, what you could see, just not essentially the full picture. And you're just there, like, oh, this is going to be great. And then you get into it, and then you realize that some things start to show up. That's what we call, maybe you can some people call it the marginal probability, some people call it evidence, some people call it likelihood. And that one starts to show up, and then you're like, okay. That one now revises the prior probability into something called the posterior. The posterior might be good, and you'll be like, oh my God, I made the right decision. And or the posterior might be bad depending on the evidence, and you'd be like, nah, I have to run. So basically, in a sense, what I'm trying to explain there is that you might have a nonlinear process that still translates back into a linear decision. And so we should keep that in mind. Right. Okay, so let's go back to a bit of talking about. So I wouldn't do the maths, but I would still try to give you some mathematical reference or words, so that when next you go to a conference or you're at NeurIPS and you hear some of these people talking, and you're able to follow those conversations. So classification is about predicting a discrete value target. Now, when we say a discrete value target, we're talking about, when we say target, let's say we're talking about something that can assume different states, right? Discrete valued different states. I know probably you've learned somewhere the difference between discrete and continuous, right? In discrete, you can say, oh, it's going to rain, it's not going to rain, or 1, 2, 3, 4, 5, 6, 7, 8, 9. These are discrete values, right? Because you have 1 is a state, 2 is a state, 3 is a state, 4 is a state, and it can only assume one of all of those states, right? Let me try to think about the weather, for instance. It's a discrete value target. In a sense, how is it a discrete value target? You can say, oh my, it's going to be rainy, it's going to be sunny, it's going to be cloudy. I don't know other weathers that we can think about. What else can we say? My emotions: I'm happy, I'm sad, I'm tired, I am angry. I did some time where somebody wanted to predict how people. So it was someone who was running for election actually, and they're like, oh, I want to know how people feel about me in a certain region. So it's like, oh, people in Lagos are not happy with you, but somehow people in Abuja like you. People in Abuja have like an aggregated sentiment, of they're happy with you. And that is, in a sense, a discrete value target where people can either be happy, angry, lovely, sad, loving, sad, or well, whatever it is, right? So essentially that, right? Binary classification is where you have two. It can only be, the people who's like, oh, life is not black and white. Sometimes I can be very troublesome. So when I'm in a trouble mode, I just be like, but it can be. I mean, somebody told me life is not black and white. And I was like, it is approximately black and white. So yeah, it's in a sense, binary classification is where you start to think about it from a black and white perspective, where you have two states, right? You hear people say, are you for me or are you against me? Are you my friend or are you my enemy? And it's like, you can only be one. So in this point, we have two states, and that is what we call a binary value target, right? And so we have these kinds of examples. You predict when a patient has a disease, given the presence or absence of various symptoms. One of the things I'd like to emphasize here is there is a linear classification here of disease or no disease, right? Or the kinds of disease. Now, the decision, disease or no disease, is a linear decision based on the states that you have. The means by which to get there might be nonlinear. The relationship between the variables might be nonlinear. Classify emails as spam or not spam. These are linear classifications where you draw a line. The method to get there might be non-linear, but it is a linear classification here. Predict where you're drawing that line. Predict whether financial transaction is fraudulent or not. I was going through my spam the other day and somebody told me that I won like $100,000 and needed to send some money. I was like, you should take it out of it. So in a sense, you want to predict that you want to build a spam detector and you're saying, okay, fine, is it fraudulent or not fraudulent? Or you want to build a financial transaction, or Flutterwave has just recently hired you. It's like, okay, we want you as an in-house ML person, and then we want you to be able to tell which transactions should we flag and which ones shouldn't we flag. Or the CBN has decided that, well, you're the next person that we want. Come and tell us what is fraudulent transactions or what is not fraudulent transactions, or which loans we should collect or which ones we shouldn't collect. Right. So here we have cancer classification, right? So I don't know if you know about cancer. There are two types of cancer. There's what we call the benign cancer, and there's what we call the malignant cancer. The benign cancer, if there's any word called good cancer, is the good one. Is the one that is essentially there but does not spread, right? Is not the bad one. It's the one that most times can easily be removed if it's in a place that is removable, and it's really not time dependent because it doesn't spread as much. The malignant cancer is the bad one. It's the one that is really terrible. I've had friends who have gotten it. Now, let's say we have a means by which we can plot this on a graph where we can put this based on some variables to say, oh, this is where we stand on the cancer human graph, right? On the cancer, potential malignant or cancer graph, which is what we have here. Let's think about it where we can project it, and then we project it on a graph. Now we want a decision maker here. And that decision maker is to put a line between the red and the blue. It's not as simple as you think, right? Here, because you see that some blue are going into some red and some red are going into some blue. This is essentially the kind of problem that you have to make. And this is that you have to solve every day within machine learning. These kinds of overlaps. And the question now is, what is the best line to draw? Where do you draw the line? How do you draw the line, right? And I said this, if there's anything you remember for those who joined late, if there's anything you remember about this course, is that this is a course for line drawing. We're only here to draw lines, right? And the question is, how do you draw the line here? Hard, because even I wouldn't know how to draw the line. I'm telling you, my technical drawing is really bad. But I think it's a detour a bit. So I'll just leave, line drawing a bit. So essentially, linear classification is about drawing that line. And there are many ways that we're going to draw the line. I will give you a funny overview. A linear logistic regression says, oh, you have to draw the line some way. A support vector machine saying, oh, you have to look for what we call the support vectors. And when you find the support vectors, you're going to say, okay, fine, these support vectors are going to tell me what is the best way to draw the line. You now have to define what support vectors are, maximum hyperplane, all that. You have another algorithm called linear discriminant analysis that says, okay, fine, let us take the centroid of the two of them. The linear discriminant analysis says, let's take the centroid of both and then maximize the line or the distance between both centroids. And in the middle of that is where the line is going to fall, right? So you have different techniques, and then the center, the center of each cluster, in a sense. That's correct. I think centroid is used because of the hyperplane, because it can be more than 2 dimensions. It can be more than 1 dimension. So there are a lot of parameters that you have to take into consideration when you're looking at it from a multi-dimensional field of view. So here we're saying, okay, fine, how do we draw that straight line? And everything we're going to do is different techniques, different ways to think about the line, what to do and how to do it, right? Does that make sense? Amazing. All right, linear classification. This is a much simpler problem, right? And this is an example of what we have to do. Here we have two lines, right? Some people will say, hey, the green line is the best. And some people will say the purple line is the best. The question is, how do you find that linear decision boundary? So let's go back to the mathematics of it. I'm saying straight line here, but in a way, we are not always going to be in 2 dimensions. So we can't say line, right? When you go for, maybe you want to impress somebody, you can say, oh, we're trying to draw the optimal hyperplane in hyperdimensional space or whatever. So but in the end, what you need to know is that we are trying to draw a linear decision boundary. So in a sense, when you have two classes, what you're trying to do is say, what is the line that separates yes from no? What is the line that separates cats from dogs? What is the line that separates angry from sad, right? And it might not be very straightforward, right? Have you ever been around, people who smile when they're angry? It's like, are you angry? Yeah, no, I'm not angry. Or people, I used to, sometimes I smile, like when I'm very, very mad, I smile. Because I just smile because I'm trying to not overreact to get. So in a way, there are people like that. And in that way, that data point might fall somewhere that we don't expect it to fall. So how do we draw a decision boundary where, a model that is still going to recognize that this guy is smiling, there's still maybe pupil dilation or something that means this person is seriously angry and we have to take cover. These are the kind of things that we need to take into consideration. I'm going to go back into something quite interesting, which is about features. Well, there are a lot of, for each of these decisions that we want to make, the data points are made up of features, right? What do we want to consider? But that is something I wouldn't go so deep into. How do you extract features? I think that we might have covered that. Now, what we're going to do here is, let's assume we already have all the features that we expect and we've projected it into the space, right? Let's say for the emails, for instance, we have the words. We just have the words, hey, come and you've won $1,000 and you didn't apply for it. Let's say we just have those words and we're able to project that into through tokenization and all of that, project it into some number-based space that is now representable on the graph. The thing is this, how are you still able to separate and give those lines? In this way, somebody will tell me the green line is the best, but yes, it is the best, but we're not doing this manually. How are we able to create that? Find the linear decision boundary. So I'm separating C1 and C2. Right. So these are the things that I was saying in the last slide. If it's 2 dimensions, it's a line. If it's 3 dimensions, the decision boundary is a 2-dimensional surface, right? How many of us can think in 4 dimensions? Like, okay, so the question is this: how many, we have 3 dimensions, which is like 3 dimensions, then there's 4 dimensions, 5 dimensions. Like, some people can only see 2 dimensions in their head when they close their eyes. Something's wrong with my eyes. When they close their eyes, they see, 3 dimensions. They see only a movie that is 2-dimensional, but some people can see 3 dimensions. They can see, all around. They can see everything happening all around. It's much more clearer. Some people can 4 dimensions, can see 4 dimensions. They can see 3 dimensions, play a movie in their head, come back, play another movie, come back, and still see all the 4 dimensions. Some people can see 5 dimensions. Some people can see 10. Okay. Some might be able to, I don't know what it's called. My PhD was 4 dimensions. That was very hard because each image that I had to work with was about 3 gigabytes per image, and then you had to think about the time dimension of it. It was super hard to even visualize what I was doing. But anyways, when we are working in 3 dimensions, we know that what we have is a surface. Some people like to call it a plane. I prefer plane. Why I prefer plane is that because I know that anything outside of the 3-dimensional vectors that I'm working with, I can just move from a plane to what we call a hyperplane. So I can I can say I have a plane now, and then I have a hyperplane, and it's still very easy to conceptualize, right? Does that make sense? Okay. I only put this slide because I want to be able to show you what it means to draw a line. How many of us remember the equation of a line? How many of us know what the equation of a line is? We did that. I think I remember doing that in SS2 for the maths. So where they tell you that the equation of a line is, I think in school then, yeah, y is equal to mx plus c. Exactly. Oh, great. Did last weekend. Oh, okay. That's a cheat though. All right, I should look for some other question. Anyways, cool. But I mean, from last week, you understand that that's the equation of a line. You're trying to draw a line where your m here is what we call your gradient, and then your c is what you call your intercept, right? And max, I actually prefer max plus c, to be honest. That's lovely. That's a new joke I would use. But what I want us to visualize here is now, when we do things in one dimension, right, it's just a precursor to what happens in other dimensions, right? You can always extend it. And that is why people use a lot of maths, because when you can think about it in 1 dimension and then push it to what is happening in 2 dimensions, three dimensions, 4 dimensions. So from the machine learning perspective, when we do W transpose X plus W naught, what we're saying here is that this W transpose is supposedly our gradient values, which is the M, and W naught is the intercept. In machine learning, we have changed that from intercept to what we call bias, right? And in that sense, the bias, many of you who use neural network or who do convolutions or who use dense nets or who are start training models will sort of have seen some of this in when you're defining your layers. But essentially, remember this formula. This formula is what is going to get you from the beginning of this entire, I don't know how many weeks your lectures are, from the beginning to the end. Everything you're doing is somehow related back to this decision boundary, not just in 1-dimensional space, but in multi-dimensional space, where you're able to say in 3 dimensions, you have a vector of intercepts or a vector of slopes or a vector of gradients multiplied by an input. You can map it back into an output called C or called Y, right? So this is essentially what we're going to be doing all through. Drawing this line that in 1 dimension is, in 2 dimensions, you have a 1-dimensional line is y is equals to mx plus c, but in multi-dimension is W transpose X plus W naught, right? Does that make sense? So let's just move on, right? So I'm going to run through this, and this is for the mathematical people, right? Back to cancer. Now, I didn't want to focus on this. And honestly, if you don't get this, don't beat yourself. I only put it there because I know that, people are going to take the slides back and then they're going to want to go through it. I don't know if you're those kind of people. I was never a good student, but I hope you're a better student than I was. So I hope that you go back and read the slides and try to understand where we're coming from with this. But I've put this there for those who enjoy mathematics to go back and look at it, right? So your input features, right? Your input features are definitely going to be what we call n-dimensional real numbers. What does that mean? It means that your input X, can I have a pen here? I'm not sure. Your input X right, is a subset of n-dimensional real numbers. Have we had a class where we've had to go through mathematical notation? So I know how much time to spend on this. Oh yeah, okay. So I wouldn't stress too much, right? Okay, cool. So it means that your features can be multi-dimensions. Let's look at a human being, for instance, right? Let's say I want a human being. I've decided that I want to describe a human being based on 4 dimensions, right? Let's say, what are the 4 dimensions I want to consider? Eye color, height, weight, and what else? Hair color. Those are 4 dimensions. So in that case, what my X, which is representative of a single data point, a single human being, will be a subset of this real number, this weirdly looking strange R. Honestly, that's why I have a problem with mathematical people. I've still been beefing for a very long time. But I realize that even I do this sometimes, but one has to write papers. And I haven't written one in a while, but this weird looking R is what we term real number, all right? And some of you know that there are 2 kinds of numbers. There's a real number and there's a complex or whatever. That's different. So this is a real dimensional number. And what we're saying is that X is a subset, that real n dimensional number. So what we're saying here is that X can be described by 4 values. One single, if n is equal to 4, one single data point can be described by 4. If n is equal to 10, and you've identified 10 features by which you can describe one human, it means that, X is equal to 10. That means for every human, you're going to represent them by 10 numbers. And by that representation, you're going to be playing in what we call the 10-dimensional space. Does that make sense? So this actually defines the dimensions, right? How many numbers you're going to use to represent that person. So I'm going to try again so I don't lose you. So let us say that maybe I should let me use another drink, right? Let me use another example. Sorry. Let's say that you want to represent, you have good egg and bad egg. So let's say you're in an egg frying competition, right? You're in an egg frying competition and you have different cooks, right? And you want to be able to have a separating line that says good cook and bad cook. And you want to evaluate everybody based on how they fry their eggs, right? But you don't want to go around, keep looking at it. You want to just create a decision boundary. You want a model that can just say good egg, bad egg. And then you're just saying, you see all this bad, I'm not even going to bother looking at it. I'm now going to look at the good ones and evaluate, right? So you need a decision boundary between good eggs and bad eggs. So what do? You say, fine, I'm going to teach this model some things that I know about good eggs and bad eggs. 1, how black it is, blackness. So let's say the first variable is blackness. If it's black, if it's very black, of course, it's bonds, right? So you might have that as, so you might have blackness, you might have whiteness, blackness, whiteness. What else can we have for eggs? Maybe it's an omelet. So you could say how disjointed. So how many pieces? Yes, brownness, maybe, yeah. You can say brownness, you can say how many pieces. So if the person provides egg, it's supposed to be an omelet. I don't know if it's omelet, they call it the flat one. If the person now provides omelet that is like different, cut everywhere, you might say, okay, that is. So right now we've identified 4 different things we're looking at, right? So what it means is that for every egg that has been cooked by a cook, or let's say for every cook, we will represent them by 4 values of their eggs. So in that sense, we'll say that each cook is represented in what we call 4-dimensional space. Okay, So outputs, so we've talked about inputs here. So outputs is like, so outputs is always going to be, also has a dimensional value, right? But it's always going to take on states, what we call states. So in this sense, what it's trying to tell us here is that our output has to be one of two states for the cancer one. Two states. So if you had three states, you would have maybe three values. So in this kind, we say the cancer is either malignant or benign. For the cook, good cook, bad cook, right? In a sense. So our input values is for the egg now, brownness, blackness, whiteness, what else did you say? Number of pieces. And for the output, it is what? Good cook or bad cook. And those are the decisions to be made. So X is that, Y is that. Now, I have mixed and matched notations in this slide, and I'm very sorry about that. I intend to correct that. But just stick to the intuition of it. The input, the output. The input is going to take n-dimensional, features. It's going to have n-dimensional features based on the number of features you're using to represent a data point. The output is going to take on states for a classification problem, whether it's, if it's only two states, then you have binary. If it's more than two, then you have what we call a multi-classification problem, right? Now, your model is going to have what we call, now we have a model parameters, right? And the model parameters here is, think about our straight line that we were doing last time. Think about our straight line. Our straight line are the parameters here, because our straight line W is what is going to multiply X, and that is what is going to give us the equation of our line. Now, think about one dimensions, but know that the same thing that happens in one dimension can be generalized to multiple dimensions. So here, our model parameters is saying, what is the value of, in a sense, the slope and the intercept in the case of a two-dimensional problem with a one-dimensional, with a line. In the case of a multi-dimensional problem where you have what we call the slope and the bias, I guess. What is the value of the slope and what is the value of the bias? Now, all of these are the model parameters, because all of this is what is multiplied with the input value of X to give you the equation of your line, or the equation of your surface, or the equation of your hyperplane, depending on what dimension you're on, right? That makes sense? So in the end, we have what we call a hypothesis function. In the end, after you have now created your line, right, your hypothesis function, right, or in a sense, when you're creating the line, your hypothesis function is the function that takes your inputs and tells you on what part of the line it is going to fall on. The hypothesis function is saying, is the one that in the end says, is this benign? Is this malignant? Where does this fall? Where does this lie, right? So in a sense, it is assigning a sign. It is what we call a predictor. I prefer to use predictor, but there's two reasons why people use hypothesis function. So one reason that I know of. The hypothesis function, especially in the case where you're doing neural networks, you are constantly revising your hypothesis. So let's say you're drawing a line, you're constantly changing the line. If you've heard of backpropagation, so you draw one line, you're like, nah, this line doesn't work. That's how backpropagation works. Draw a line, this line doesn't work. We change it small based on what we saw. What doesn't work, we change it. And you keep changing until you get to a final line that works, that becomes your predictor. But in linear problems, or sometimes you have what we call a closed form solution. Now, I'm not going to, like I said, I'm not going to bore you with maths. I have 3 minutes. I'm not going to bore you with maths, but in a closed form solution, you don't have to go through backpropagation. So there's always this predictor hypothesis, but I'll stick to predictor here. All right. Cool. Now, yeah, so basically, let's go back to our predictor, right? No. So let's go back to our predictor here. Our predictor here is the decision maker, right? A predictor here is the one that says, this is benign or this is malignant. Every thing that we're trying to do is to create this decision maker in a way. And our decision maker is a line, not necessarily straight, but a line that is able to separate those two classes. Like we said, we are looking for a decision boundary. A decision boundary here is created by our predictor being able to say benign or malignant based on input features that we give that maps to output features that are discrete valued and sometimes binary valued, right? If that's too mathematical, I will step it down. Just feel free to put in the chat, step it down if you want to step down the maths, right? So essentially, what do we do, right? So to make a decision maker, we need what we call a loss function, right? And a loss function is quite interesting, right? A loss function here, when it matches, right? When it matches, when we say that the predictor, let's say the predicted value is, if you say it's benign and it's actually benign, then it should give you 0. And when you say that it is not benign and it is actually benign, it should give you 1. So in a sense here we have, and I need you to follow closely here, right? What we're trying to see is our predictor, which is H0, which we have defined, which is supposed to be able to predict and help separate into those two classes. Is it doing a good job, right? And our loss function is defining whether it is doing a good job. Now, the loss function, as you will see when you start to go into nonlinear, is one of the foundational elements of machine learning. But please retain the intuition here. The intuition is that when our predictor is making a mistake, it penalizes our predictor. And when our predictor is close or is doing a good job, it doesn't reward, but it doesn't penalize, right? There are other loss functions that reward. And when you want to get into maybe rewarding loss functions, you start to go into the realms of reinforcement learning, and maybe you start to go into the realms of losses such as triplet losses, but that is way complex outside of the purview of this. But just think about it. Our loss function is the teacher that is coming to evaluate our predictor to say, is our predictor doing right or our predictor doing wrong? And here, if our predictor gets it, not depending on whether it's close or not, if a predictor is able to say, oh, you're on one side of the line, you're on another side of the line, and it's able to get it right, we give it 1 if it gets it wrong. So we penalize it with 1, with a value of 1, and we don't penalize it if it gets it correctly. And I know you have to invert a bit of your thinking for this, because there's a difference between the cost function, the loss function, they're similar, but just remember this. We don't penalize if it gets it correctly, but we penalize it if it does not, right? So this is how our loss function is going to be. How many of us know what this kind of function is? Look at it. It gives it 0. And 0 when it does. So function is this? Step. Oh my God. That's what told me. I should have made it more complex. Function. This is what we call a step function. It is bad. It is reasons why a step function is. A lot of things we're going to be doing in machine on what right? The underlying criteria function to be used in machine learning is what we call piecewise. And how, but this function, this step function is not piecewise differentiable, because at some point on this differentiability curve, you're going to have values that go to infinity, because one of the criteria for differentiability is what we call continuity. And that means that there cannot be sudden jumps or sudden changes. Here, because when we have sudden jumps within a differentiability curve, it's going to show up as infinity values. So because this guy just jumped from 1 to 0 like that, the large discrete jumps, which are not permitted in differentiability curves, this function is basically unusable. Because a way by which we backpropagate, a way by which we correct our hypothesis functions is we use what we call backpropagation. You get into that. We use backpropagation, and this guy cannot work with backpropagation because you cannot differentiate it. Your differential curve wouldn't make any sense, right? Why? Just remember the intuition. You cannot have sudden jumps because when you do differentiate sudden jumps, it means that there is no piecewise continuity. There's no continuity. And since there's no continuity, you're going to have infinity values showing up in your differentiability curve. Right? Does that make sense? I don't know that's anybody. I'm not showing you the formulas. I'm just, trying to carry along the intuition. You're going to go deep into backpropagation. That's outside the purview of this particular lecture. But I just need you to retain a lot of these things, right? Just think about it. Just keep it in your mind. So the loss function is very important because it's a loss function that evaluates our predictor on whether it's doing a good job on separating between the two classes. And our predictor is what we're trying to create. So we're going to talk about two kinds of predictors. We're going to talk about SVM. We're going to talk about logistic. Forget those guys. All those guys are trying to do is telling you a different way by which to create a predictor. The loss function evaluates the predictor, but all of the difference between those algorithms is, oh, I have a different way by which you can draw a different line and a better line. The loss function is still there to evaluate that, right? So because of the optimization problems we have with with step functions, right? A lot of times they're not used, except it's in non-differentiable problems, or except we have closed form solutions. And sometimes we do a lot of times, especially in linear, where we don't have to do any backpropagation. Is the 0-1 loss. It's not convex, and it's very difficult to optimize. Don't use it if you do not have to. What's the word? Don't use it except you have to. And there are alternate losses, and that is all this causes. There's logistic loss, which is here, which is trying to say, okay, fine, I'm going to draw a separator, but it's going to be different. It's not going to have sudden jumps. So if you see the loss, the eventual loss function of the logistic loss, you see that it doesn't jump, it gradually goes down. And of course, the decision boundary is going to be somewhere within the line. You have the exponential, you have the hinge. The hinge loss is used in SVM. I wouldn't go deep into that, so I don't confuse a lot of us. The logistic loss, of course, is used in the logistic regression, which is also a classifier. And we have the exponential loss, which we're not even going to cover anyways. But we're all going to we're going to focus on the intuition. So what is the machine learning problem here? The machine learning problem is this. You have an X, which we've defined as an input value, right? You have a Y. You have a predictor that gives you a prediction on an X. So the prediction on the X is two classes, right? Two classes, benign or malignant, good or bad. Your predictor takes the X and gives you a prediction, and your loss function evaluates how close the prediction is to the original value, right? That's this entire mathematical function. And you do that over, and don't forget what we said. Our loss function says if they are the same, we penalize it as the one you look at the stepwise function. If they're the same, we give them 0, we don't penalize it. And if they're not the same, what do? We give it 1. Now, what we're trying to do is that we're saying that for all the values, for all the samples that we're trying to evaluate, we are looking for the predictor that gives us or the predictor with different parameters, or let's just say the predictor that gives us the lowest loss value. Because don't forget, if they are the same, it is going to be 0. If it's not the same, it's going to penalize it with 1. So you want to minimize that and make sure that it's as low as possible. So you're looking for the predictor, you're looking for the line in this case that minimizes this, that minimizes the distance between what you predict as the class and what the actual class is. Have I lost anybody? I mean, if I've not lost anybody, yeah, I'll be so happy. It's usually where I lose people. Let's go back to the story. Let's start the story again. We understood that we had X values. To create the X values, we had to get data points that explain the X, and that was where we're talking about the human, the cooks, how do we evaluate the eggs of the cook, right? Good or bad? Here is cancer, where we're thinking about malignant cancer or benign cancer, right? So we had malignant cancer, benign cancer. How do we say one is malignant or one is benign? That is the class, that is the state we're trying to predict, right? And then we have the input features, which are basically how do we evaluate the egg? So we talked about brownness, we talked about whiteness, blackness, we talked about number of pieces, right? For maybe the cancer, we'll be looking at maybe the size of the image or the mean area curve or something around that nature that helps explain whether the cancer is malignant or the cancer is benign. For cooks is something else. And the entire task that we want to do, okay, somewhere I'm coming. The entire task that we want to create is to what? We say we want to draw a line. And we say that we can draw different kinds of lines based on what we call the parameters of the line. The parameters of the line we had previously defined as the slope and the intercept of the line, right? Where we had said y is equals to mx plus c, and then we say that is generalizable to other dimensions, because now we're trying to draw a separating line in the binary case. So our task is to say, what is the best line that we're trying to create? And that best line is defined by the parameters here, which is, of course, a subset of, which in our parameters here is just our slope and our intercept. In this sense, we now say that we can have different kinds of lines based on what we call our predictor. So our predictor function is the line. We can represent our line by a predictor function. And our predictor function can have different parameters for different kinds of line. So our proper line, or the best line, right, is what we're trying to create. Now, the question is, how do you know the best line? We don't know how to know the best line. I mean, physically, we could look at it and say that the green line is the best line. We can say but someone else can argue that the purple line is the best line. But how do we codify this? How do we make this mathematical? How do you create this into a mathematical equation where we know, or our mathematics can know, or our model is able to evaluate and say that this particular line is best for this particular problem, and it optimally separates between good and bad? Now, we have now brought our problem down toward finding the best parameters for the line that is able to separate between two classes. But how do we get the parameters? Don't forget that these parameters are intercept and slope, right? Now, we say that the best way to evaluate how well we're doing is through what we call a loss function. And our loss function here is saying, okay, if we look at these previous ones here, right? Let's say we pass it through our evaluator. We are able to penalize for how well we're doing based on the line we've drawn. For instance, here, the purple line, right? These purple, or this particular blues that fall into the other side of the red, there are blue dots here that fall on the other side of the red. What's going to happen? Because this line is putting them along with the red, for each one that falls on that side, we're going to penalize with a 1. We're going to add a value of 1, right? If it is properly classified, is going to have 0, so we're not penalizing it. But it's improperly classified. We're going to have what? We're going to add a 1. Now, what we've done is we've created another value called what we call the loss function. And our loss function is trying to evaluate how good is our line that we're drawing, right? And what it's now saying is that the way it's going to evaluate that is that it's going, after we've drawn the line, it's going to look at that line and say, hey, some of these things are falling on the other side. And for every one that you don't get correctly, I am going to give you, in our mind, we can think of it as I'm going to deduct -1 from your score. But in this sense, because the optimal score is 0, the best score is 0, I'm going to add 1 to you. So you get 1. Right? And for even this red one that falls on the other side of this purple line, I'm also still going to add 1. And here we can see that the green line can already be seen to be doing much better, because with that one, of course, you're going to have a final score of 0. And don't forget, 0 is good. And for this one, you're going to have, because of all the points that fall on different sides, what you're going to have is you're going to have maybe a value of around 10, which is bad. Right? So the loss function is trying to say, I'm going to look at different lines, different parameters, and I'm going to say this line is better because it doesn't violate the conditions. Right? I hope I still have people. Now, that's what our loss function is doing. But this particular loss function that we have is what we call a step function. It would have been perfect, but it's not good, because a lot of things we're going to do has to do with differentiability, especially when you get to things like backpropagation. Most of the things in machine learning has to do with differentiability. We have to be able to differentiate. We have to be able to backpropagate. And this line is non-differentiable because it doesn't have continuity. And it doesn't have continuity because there are jumps. There are sudden jumps, which is not good for differentiability. And what we mean by sudden jumps is suddenly jumps from 1 to 0, which is going to create a huge mathematical problem for us. It's going to cause huge mathematical problem, huge numerical instability. It would have been perfect, but the tools we have in mathematics cannot handle this. So what do? We need to find a loss function that still penalizes the deviations of the line we draw, but is also differentiable, right? So everybody, just the same way everybody has different, when first time I left Nigeria, I realized that everybody doesn't use the same keyboard. It was one of the worst things I had to experience. Sorry, Samuel, I'm coming to you. But this is the same thing here. So everybody now says we have a way to solve this problem, right? There are people that solve it using what we call the logistic loss, which is a loss that is both differentiable. It is differentiable, but it also still penalizes deviations. Some people use the hinge loss, which is what SVM is built on, which still penalizes these deviations too. And there's the exponential loss, all because we're trying to get around the gradient descent problem, which needs convexity, which also needs different, and convexity means it has to be differentiable. Sorry, I just gave a long rant, but do you understand?
Okay, please, I think one thing that is confusing me right now is just my inability to read and understand the formulas, understand? So I wanted to know if there's any there's like any PDF textbook that you can actually recommend that actually break down this thing to a smaller term for us. That is why I raised my hand.
Oh, okay. So yeah, I would send those recommendations in. Hopefully, I also hope to get reminded. I'll send those recommendations in. Honestly, the formulas are, especially if it's your first time, the formulas are intimidating. Don't be intimidated by them. Try to retain the intuition, like I said, but keep looking at the formula. At some point, it will come to you. I would honestly tell you that until my master's, I hated looking at mathematical formulas. The thing about it is, as you keep looking at it and you keep relating it back to the intuition, you start to get it. the logistic one here, I can already tell you is that, oh, it's going to take the predicted values. It's going to then multiply the predicted values by the negative of the supposed y value. So if the y value is supposed to be 1, let's say we said benign is 0 and malignant is 1, and our predicted value was 0, for maybe it's supposed to be 0 and it predicted 0. So you say 0 multiplied by minus 0, you take the exponential of that, you add 1, you take the logarithm of that. That is going to give us a predictor, that is going to give us a loss value that is differentiable and also is able to penalize if our model makes a mistake of putting benign and exactly 1 is equal to 0. If that is let's not jump. Let's let's look at 2 classes first. But a lot of the things that we're looking at, honestly, moves on, is also applicable when we have more than 2 classes, right? Same application. You use softmax. For SVM, you use what we call the multi-class SVM. And a lot of times it is what we call the one versus all. So you now have multiple separating lines as opposed to one separating line. So you have multiple separating lines for different classes, right? So if you had like, I'm trying to visualize that, but if you have good, bad, ugly classes, you have good versus the rest, ugly versus the rest, and bad versus the rest. So this kind of, so at this point, you now have those, 3 separating lines. That makes sense? Good. Okay, so logistic regression. So essentially, like I said, I'm not going to, there's a code part of it, which, the lab is going to help us with. But like I said, if you want me to come and do mathematics, you can always maybe during the week find, some 30 minutes or ask me to record a mathematical video for you. I don't mind, send that. I'll do Loom. I don't know if you know the software. I'll do a Loom video and send around. But the thing about it is here, please retain the intuition. Now, we're drawing a line, right? A line is what we're drawing, but what we have is we're trying, not a line, we're drawing a decision boundary. Now, but we have, don't forget what I said here. Don't forget what I said here, where I said what we're actually trying to do is we have to evaluate our decision boundary through a loss function, right? We have to evaluate our decision boundary through a loss function, and our loss function has to be differentiable because we had this guy and this guy wasn't differentiable, but we want something differentiable. And so we came to what we call the logistic regression. And just remember this, logistic regression is, in a sense, using what we call the logistic loss, and it's using a linear hypothesis function. In a sense, I'm going to try and explain this in English. It is essentially trying to make the distinction where one class is 0 and another class is 1. And instead of having that hard boundary like we had with the binary loss or with the stepwise loss, it essentially makes it differentiable. So look at this loss function here. There are no abrupt jumps. It is smooth. It is smooth sailing. It is no abrupt jumps, and so this makes it differentiable, which means that it makes sense in a backpropagation point of view if we want to use that, and also means that we now have a convex function with which we can optimize. Okay, so in a sense, now this is what we're trying to do. We have now replaced, sorry, I keep going back. We have now replaced our machine learning problem here with the minimization over all the set of samples, right? The minimization over all the set of samples based on a given loss function. Now that we have the loss function, we're now trying to say that the best line here is the line that actually minimizes this. That minimizes the log of 1 plus the exponential of minus y, the parameters multiplied by, which is the predictor function, multiplied by x. Have I lost anybody? So, right. This is something I put for us because I know we have a lab. So I've put this, right? And you're going to, after your lab, you can try this at home, and then you can try to see, you have the exam score, you have 2 exam scores, and then you have whether the person was admitted or not. And then you can use logistic regression. There are, of course, in Python, there are already, what do you call them? Packages that do that for you. You can use SciPy. Please use SciPy. I'm sure you see that in your lab, and just try this on your own, just to get a feel for how to do this in reality with a problem. Here we have an exam score 1, exam score 2, admitted or not admitted. SVM. I want to spend time on SVM because now there are a lot of intuitions that come with SVMs that we want to retain in our mind. And honestly, some of the ways that SVM solves this problem has been carried along. So in a sense, we have what we call the hinge, which was the general concept. And I remember a couple of years ago when I was doing things around generative AI modeling, and there was a lot of hinge that was coming up. So even the concept of SVM was carried on from a simple classification to really complex ways to approach problems and solve them. Even in your life, I mean, there are things that you understand in your life, and then you make decisions. I am a fan of anything I learn. If I cannot apply it on a day-to-day basis, then it's not worth knowing. And anytime I see people on Instagram saying, I did engineering, I've never used the YDX, I know that these are the kind of people that I never want to hire. Because I use the YDX every day. Everybody uses the YDX every day. We don't just know that that's what we're doing, but that's what we're doing. We're measuring change. So every time where it is easier to measure how something changed than to measure how the entire thing is, we're doing the YDX. If somebody tells you, oh, he was a good boy, but now he's becoming a bad boy, they're just telling you that the guy is having a negative differential that is not going well. That's what they are saying, that in his attitude towards life or his behavior, the differential is going towards the negative. That's what they're saying. So I like to talk about the intuition around what we're saying here. So I'm going to focus here. And of course, it's supervised learning used for classification and regression sometimes, but what are we trying to do? We're trying to find the optimal hyperplane that separates the class into data, that separates the data into classes, right? And what does that mean, optimal hyperplane? And that's the only problem I have with SVM when they say optimal. But in a sense, what it means is we're trying to find the best line. We're trying to find the best line. Don't forget we said that in 2 dimensions, in a plane more than 2 dimensions, the hyperplane. So we're trying to say what is the best line. We can have many lines. Like for instance, in these 2 places, in these 2 classes that we have here, we can have different kinds of lines. We have a distance between them. We can draw one line one way, another line another way, but which one is the best? How do you know that this line is the best? And of course, that's what our loss function is doing. So SVM is incorporating a loss function that claims to say, I know how to find the best hyperplane. And I'm going to show you a technique by which you can find the best hyperplane called using the concept of support vectors. So while logistic regression is saying, oh, just plug in my loss, SVM is saying, oh, I have a different attitude towards finding what the best line is. So there's a couple of things we want to define. The margin is the perpendicular distance between the closest data points and the hyperplane. So for instance, the margin in this, you have these 2 vectors, these 2 points we call the support vectors. The margin is the difference, is the distance between the green here and the separating line, and the blue here and separating line. That's what we'll call the margin, right? This green that has the arrow pointed to them and the blue are having the arrow pointed to them, we call them the support vectors. it means that they are like critical in, in what makes, in how we make our decision. And let me see. Oh my God, time is flying. Why? Yep. So what he's saying is that the best optimized line is the one that has the maximum margin. So it's like, oh, it has to be far away as possible from what we call the support vectors. And I mean, some of you will start to visualize that, oh my God, sometimes the data is intertwined together, but then in support vector machines, there is a penalization for that, right? So what you are trying to say is that if you're trying to separate two classes, you need the one that goes right in the middle, but maximizes the distance between both classes. So the line must be as far away from the two classes as possible while still separating them. And the way you calculate the distance to both classes is through what we call the support vectors. Bring back to real life, right? When you want to make a decision with many variables, right? Many things. You look at what is the most defining variable, right? Let's say you want to go and look for a contract in Nigeria, and suddenly I realized that, I don't know, last year when I did this course, I had hair, right? So I had hair, and I realized I had dreads, and I realized that I wanted to start working in Nigeria full time. I wanted to start doing some things within the Nigerian space, working with companies, consulting and all that. And I had to think about it after I was arrested 2 times. What is my support vectors? To work in this particular economy in this country, I don't get shot one day. I'm walking into all these offices where people will not even answer you based on, they just look at you, just I don't know, Yoruba people say, or say Mama Buruku is a bad boy. Yeah, so at some point, yes, that, which is very funny, my hair became a support vector that was pivotal in the decision making of, whether I should, what I should do. So in a sense, you have to look at those features that become, or those points that become the defining points in your decision making, drawing that line. Good. So this is how you look at it, right? So you have this line here, and what you're trying to do is maximize. So the optimal line is the maximum between the one that maximizes the margin. And don't forget that I said the margin is the distance between the support vector and the line. And I've already defined what the support vector is. Now I'm going to go through the intuition of this. Keep in mind the intuition, right? You might not get the formula, but keep in mind. So in the end, we have this very complex formula. And this very complex formula is what actually does that for us, right? I know that I promised that no maths, and I know that this might not be something you get within this time, but also feel free to reach out to me, and then I can try to discuss this further. But this is what SVM is trying to optimize. Think about it in your mind, that is the support vector. That we're doing a support vector, we're doing a margin classification that tries to maximize the margin between the support vectors and the optimal hyperplane. And this is the minimization that does that for you. So when we go back to what I was saying before, this is the loss function that does not only penalize for the line being a good line, being able to say this is black or white, or this is benign or malignant. But what this also does is saying that I'm not going to evaluate you only by how you're able to put it in one class or put it in another class. I'm also going to evaluate you on how much of the margin you take into consideration, right? And this regularization is just to ensure that you don't have wild values on your as your parameter values, so that you don't do too much of an overfitting. Okay. I decided to add this for people who are already, very sad. I'm doing, and this is to tell you that this is how easy it is to train it. in Python? How many of us are familiar with Python? You can write Python code. Python, great. So yeah, this is how easy it is to write this. I'm sure it'll come up in your lab. This is using SciPy and scikit-learn, and this is how easy it is. So that is why I said it's easy to get it done. The intuition is the most important thing. You might not ever remember the formula, but you should remember the intuition. Honestly, I a lot of times forget the formulas, but the intuition keeps me going. Good. This is also an exercise that you should try at home. And that's why I try to learn. I put the groundwork. Please try it, have fun with it. If you want to send it to me, send it to me. If you want to discuss it with me, discuss with me. But use scikit-learn, try it, and enjoy yourself while you're doing it. And that is very important that you do enjoy it, right? There are a couple of things that I just want to add. I think I have 5 minutes, but I'm going to power through. Linear discriminant analysis. Now, I'm going to also focus on the intuition for this one. It's also a supervised learning, machine learning technique that aims to solve the same problem that support vector machines and logistic regression are solving. How do we know what line is the best line, right? Logistic regression is saying, let's evaluate the line, based on a modified version of the stepwise function, something that is differentiable. Support vector machine says, okay, yeah, let's add some constraints to it. There has to be the constraints on the support vectors. There has to be a maximum margin. The best line is the one that maximizes the margin, not just any line. It doesn't just have to separate them into classes. It also has to maximize the margin, which we understand. Linear discriminant analysis is saying, okay, we have a different way by which we will solve this problem. And you're saying, okay, fine. We have these features, right? Let us maximize instead the between class variance while maximizing the within class variance, resulting in optimal class separability. That's interesting. That's grammar. But let me explain what it means. It means that it's saying, okay, fine. We have malignant and we have benign, right? What we want to do is to say that the best line is the line that maximizes the distance between the centroids of both classes, right? It maximizes that distance, and but in the same vein, it minimizes the variance within the class. So the variance within the malignant cluster will be minimized, but the variance between the malignant and the benign will be maximized. So in a sense, what it's trying to do is saying that I'm going to draw an optimal separation boundary, or I am going to say the best line is the line that maximizes this, right? And so in a sense, we can then say that this class here has been separated into two classes in the way that both centroids, the distance between both of them are maximized. Now, I know that you guys have probably thought about, I don't know if you thought about PCA, but then there's also a lot of things around difference between PC and LD, and I've put this slide for you to reference back to it when you do need it. But all you need is the intuition, the centroid, the center. If your centroid is too big, just say center. All of them have a center. So the ones that are together, the center should be small. So if what it's saying is this, right? Let's think about it like this. In a sense, I do agree with you. You may change the classification, making some benign or more malignant because there are overlaps. So what you're trying to say here is that this essentially works when there is clear separability, right? And that is true. And that is one of the reasons why support vector machines is still very much in use today, because it accounts for overlaps, right? This does not account for overlap. And so that's why a lot of times it's not being used, and sometimes it's not even taught anymore. But if some of you go on to become researchers, the thinking around linear discriminant analysis will help you in formulating solutions sometimes to problems that you may have, right? And so that's why it's here. Got it? Oh, so I'm not going to go through this. This is here if you want to try and do it on your own. Okay, and so we get to perceptron. So this perceptron is actually quite interesting, right? The perceptron is the foundation for machine learning, right? And the perceptron, think about it as, a single activation function. I don't know if you've thought about machine learning that now tries to make a decision based on input features, right? And so think about it from a point of, I have a neuron, and I know that I'm not going to go really into this because there's still classes for you, and there's a lot of them. But just think about it like it receives inputs, multiplies them by some weights, and then it has to output a binary value of yes or no, this is good, based on some activation function. So the activation function is what takes the output from the neuron and makes a decision on it. Now, what we've been able to do in deep learning is that we've been able to take like 1 billion of this and put them together, and then we call it ChatGPT. All of this making micro decisions, linear decisions as we go. But just have this at the back of your mind. And one of the reasons I put this here so you can have this at the back of your mind, right? Okay, I have come to the end of my lecture, my submission. I hope I did not bore you. Thank you very much for listening.